All right, so we're taking a look today at pages 12 and 13 of the equilibrium packet. Not too difficult here. This should not take long. Just go ahead and get rid of me. Take a look at these problems here on page 12. It says the initial concentration of reactants and products is given. So these are the initials. It says calculate Q and determine the direction that will be favored. So they give you K. Remember, if Q is equal to K, that's at equilibrium. If Q is less than K, then the forward reaction is favored so that Q gets to K. It's all about getting back to equilibrium. If Q is greater than K, then that means we have too much products. Remember, the K is products over reactants, so we've got to favor the reverse reaction so that Q gets back down to K. If Q is found the same way as K, you take the products to the power of the coefficient divided by the reactants to the power of the coefficient. Remember, ignore anything that's not gas or aqueous because that becomes 1. So that means we get, calculator, it's hidden, here we go. So we take H2, which is 1, so we take 1 cubed, times N2, which is 1, divided by 0.2 square. So it gives us 25. So that means that we're above K, so reverse is favored. All right, so you'll go down through there and work some of those problems and do basically the same thing. That's a lot of extra practice. So here we're going to talk about KSP. And KSP is found the same way that Q is. KSP as the solubility equilibrium constant. So if we recall, at certain temperatures, there's a certain amount that will dissolve of particular soluble salts. So here we have In2S3, and that's going to break down into this right here. So the KSP expression, since this is solid, it will be In, oops, that's a weird N, 3 plus, to the second power, times S 2 negative to the third power. All of this would be over 1, but it won't matter. So let's try one more. Al 3 plus and PO4 3 minus. Now the cool thing about this is for every one of these, you get one of these. So 1 mole of, if you have 1 mole and it all dissolves, then you'll have 1 mole of particles of Al3 plus and 1 mole of particles of PO4 3 negative. If we're looking at this right here, it's a 2 to 1, or 2 to 3. So these concentrations, this one will be 2 times X, and this one will be 3 times X. So imagine if we have 2 moles of In2S3, that would actually give us 4 moles per liter for the concentration here, and 2 times 3, which is 6 moles per here. So let's take a look down here at what we mean by changing those concentrations. So this one's a good one for us. So the KSP is equal to PB 2 plus and Cl negative squared. But the concentration here is going to be different. The concentration here is going to be X. For every one of these, we get X of these. And the concentration here will be 2X. Because one of these breaks down into one of these, and one of these breaks down into 2 of these. So for every one of these we'll get 2 of these. And it gives us the KSP here. It says it's 1.7 times 10 to the negative 5th. So that is the equilibrium constant. So we will go ahead and plug that in there. And we will take, and oops, I almost forgot the 2 squared here. So what that's going to be is 2 squared is 4. X squared times X will be 4X cubed equals 1.7 times 10 to the negative 5th. So we take 1.7 times 10 to the negative fifth, we divide it by 4, and then we take the cube root of it. Let's put 3, answer. Boom. We get 1.62, actually 1.6 times 10 to the negative second on that. So here, for every one of these, we would get 2 of these, so that would be 2x for the copper, 2x squared for the copper, and 1x for this. See that subscript there? When this breaks down and separates, we get 2 moles of copper for every 1 mole of copper 1 sulfide. So if we take a look here, the last type of problem is they give you the molar solubility, which is what we just calculated. So let's take, and we are going to find KSP. So we know KSP equals Al3 plus times OH negative to the cube. Now the molar solubility is that X. So this will be 2.9 times 10 to the negative ninth, right? And then what we have here is 3 times 2.9 times 10 to the negative ninth, and that's cubed. Once we multiply that through, right, I have that 3 because of the 3 there. Remember, this is still just the concentration of OH. But the concentration of OH is 3 times the concentration of Al, because there's only one of those there. So we take 2.9 times 10 to the negative ninth times 3 cubed times 2.9 times 10 to the negative ninth. And we get 1.9 times 10 to the negative 33rd. And that is the molar, solubility product constant for aluminum hydroxide at whatever temperature this is. Very cool. So if you would just work through those problems, 14, shouldn't take you that long. I'll post the answers for that probably by the end of the day on Monday. Thank you and have a great day.